Right, C495. This is kind of a recap. So far, we had some kind of opportunity to generate the geometry of some tower last week. So we play with some Rhino and Grasshopper script to generate the geometry for 40-story building. Basically, this is kind of graphical interface script to generate some sort of 3D geometry. Since we are working on 40-story tower, we create two geometry. One is ellipse, using ellipse as a plate. The other one is a rectangular base. So since we generate the geometry, we can copy those geometry based upon the total the floor, the building height, which is 15 feet times 40, so it's about 60 feet tall. And the long story short, this script, once you generate the geometry, and in order to do that, we use copy and rotate and loft to generate the surface. With the surface, the information we using contour command, so slice it every 15 feet along the height in G direction to get the outline of surface. So it's the edge of the slab representing the line of slab. That is our reference line to generate the edge of slab elements, and also we use it to generate column. Since building is twisting, sometimes it's hard to draw the sloping column. So sometimes this parametric script is really efficient if you can generate some pattern, and it's most likely mathematical, but I think this is worth it to everyone as a civil and structural engineer who actually seeking the structural engineering, the career path. I want you to pay attention and learn as much as possible. This course is just introductions, so I just hope some of you really have some kind of the interest, find some interest, and continuously develop your skill. All right, so based upon these two script, one is ellipse, the other is rectangular, so it's a fast forwarding. So last kind of commands, polyline, when you click it, you see that this is ellipse, edge of slab. I'm gonna bake it to the layer 1, right? The second one, when you click it, this is sloping column. I'm gonna bake it layer 2. So when you select it, so you see that those line is all highlighted. The second one, the right, is simple rectangular geometry. I set it up some base as 120 feet by 150. I didn't twist it yet. Maybe can we rotate it or just leave it as 90 degrees. So rotation degrees is 0. If I rotate it, let's see. Okay, it's cool. 90 degrees. See that? You can visually, real time, see that the geometry is spinning based upon angles you want to rotate it. But for now, I'll leave it as a vertical for now. So I'm gonna bake this one to other layer. Just a column to the layer 5. Let's see, I have all right. Seems like, do I have sometimes this white line. All right. Oh yeah, this polyline sometimes let me redo it. I'll just, for the slab, I'm gonna use a polyline, bake to layer 4, and the column, this vertical polyline, I'm gonna explore it. This segment is curved, so I'm gonna segment it. So let me see. can I select by individual? All right, okay. Assume everything is ready, so I'm gonna select, but make sure you really set up the unit because this is tower is in fit. I'm gonna export this. Oh, hold on. Did I select it? Select this, export. Where do you select? Oh, the button is disappearing. Where did it go? Okay. Export. Okay. All right. This is ellipse. Okay, hold on. And rectangle, right? Tower. I export it into the DXF file. All right. So, okay, let's see. We have, okay, I've been working on it. I'm gonna be open as a new file. So when you start the ETABS, you just follow along, and I'm gonna just choose the blank, so nothing is set up. But things, so see that fit unit, you need to cross check always unit, should be consistent, unit as a fit. I'm gonna go file, import that DXF file. So, okay, ellipse and rectangular tower, right? DXF file, I'm gonna import it. So for to tower, I export into the 4 layers. Should be fit. All right, when I bring it, you see that? Let's see, everything is okay. So every floor is 15 feet. So DXF is interpolated and into the ETABS. So they registered a typical floor to floor height, total 40-story building, and at the top is 600 feet tall. Let's see. All right, asking to save the file. I'm gonna just type it. Okay. So right there, let's see. All right, so here is a geometry. You know, a typical tower. I mean, geometry is not like in this simple, but there is some thought of building and has various slab geometry, and in order to generate all geometry, I think you need some kind of tool so that you can use your knowledge and you can make something more efficient workflow. So since I've been practice testing more than 2 decades, I wish I could learn this. So I just figured out up to this point, because this is most of the time consuming the process in order to build the 3D geometry. Sometimes as a structural engineer, in practice, I was given some 3D Rhino file. Sometimes I was given some AutoCAD every plan. Sometimes Revit 3D. So it depends on what I'm given. So I should be able to figure it out to generate 3D building geometry. So obviously this saved my a lot of effort and time. So this is kind of, I think, at least the skill one all structural engineer in practice should have for your better career path. All right. Obviously, this actually we use a default the section properties. Nothing has been set it up, but if you're interested, I mean, automatically since you follow 00 at the base, the ETABS provide right the pin connection at the bottom, which I think this twisting tower might not be the stable, but we can run the model. Oh, since I imported the bottom, which we don't need it, right? Since because this is tilt twisting, let me just put it in 3D or put it in the base. I'm gonna make a fixed condition and run it. So I'm gonna assign the joint restraint boundary condition as a fixed, and based upon the default section properties, I'm gonna test run and see how the ETABS doing the gravity load takedown. Obviously, there might be some internal instabilities, so ETABS showing some. All right, let's see something. It makes sense or not? Okay. One thing I'm gonna check this. What kind of section property? Oh, deck one. Okay. So deck one is really deck, metal deck properties. So I'm gonna reassign to slab, two-way slab properties, section slab. Slab one is default is 8 inches two-way slab. Because deck has doesn't have any bending stiffness, so seems like ETABS give us the warning sign. So I used 8 inches slab as a two-way slab, so internally they mesh the plate based upon your supporting point. I will show you later. Okay, this take a while. Oh, no second. Let me see. Okay, you're creating an analysis model. Oh, wow. Probably number of mesh is pretty too small. Well, plate is relatively big. Okay, running. Okay, it's running. So first thing the structure engineer should know is basically we need to understand gravity. I know that our human body and a building is same as our human body, so everything is vertical. They're anchored at the base, so all the weight above the anchor point base is right experiencing some gravity force. So each floor has their own self-weight from the slab and column and beams. It carry their own weight. So all the object on Earth, right, experiencing gravity force. So that means the building like this, standing upright, and the column here is all the column we have supporting those gravity forces should experience the compression forces. Wow. Yeah, default modal analysis on always. So I'm sure this one's gonna show some a long period time. I'm gonna just pause and wait. Alright, so ETABS finished the analysis. Okay, next time I'm gonna turn off the modal analysis. This is not for the dynamic analysis introduction. This is just a static gravity load takedown. Since once the ETABS analysis is complete, they automatically show the displacement in dead load, which is self-weight, and usually dead load and live load is preset, so automatically they run for dead load, which is including self-weight of the structure. We didn't assign any load for live load, so you see now some dead load displacement. At this point, we're not kind of interested in looking at displacement. I just want you to show basic load takedown. Since I mean these columns, all right, is supporting the slab, 8 inches slab, 40-story tall. I mean your guess is something is straightforward, no brainer, right? The column should experience a compression, right? So here is everything is vertical, right? Vertical. Red color means compression forces. Since it's a kips, wow, 3,000 kips, wow. Yeah, this is 8 inches slab. So right, obviously at the top, the actual compression force is small, but as it goes down, you see that the column is experiencing taking more forces, right? It's common sense. Now on the left side, elliptic elliptical towers are twisting, so there will be more complex behavior. You see that compression and tension is, I think, I'm not sure, I don't think this building is stable yet, right? Some column is experiencing compression, the other one is tension. So based upon that gravity load takedown, gravity load, I think this building is not stable yet, which this is not our intention to explain that which building is stable or not. This is just for introduction of the geometric conversion from Rhino Grasshopper to the ETABS by using the XF file. This is basic introductions of the ETABS run to check the initial static analysis due to the self rate, which is cool, right? So, I mean, this is kind of basic, the gravity force. In order to design the structure, right, we need to understand all this gravity load paths, always top to bottom, right? So I want you to just practice, even a simple model. It doesn't have to be 40-story, but anything. So we need to get used to this so that we can move next step. All right, I'm gonna pause it, and we're gonna I'm gonna just record it another small introductions base study model. All right.